All right, so let's get started. First of all, hopefully you had your homework out. Your sub should be checking your Lewis structure homework and your VSEPR activity worksheet. You should have done part one for both tasks. So if you have not done that, please get your homework out and make sure the sub sees that you did both the worksheet and the activity part one. If you have done that and you have checked, you can now begin this video. So today we're going to talk about VSEPR theory, and we're going to do kind of an activity via video. And we are going to talk about something called intermolecular forces. All right, your homework is to complete part two of the Lewis structure worksheet. We're going to do part two of the VSEPR worksheet in class together. So get that out, make sure you have it available because we're going to be filling it in. And then your homework is to complete part two of the Lewis structure worksheet. So let's get started. First thing before we get started, we need to define VSEPR theory. VSEPR is an acronym that stands for valence shell electron pair repulsion theory. So what that means is the electron pairs on an atom, we know electrons do group themselves in pairs within orbitals. The electron pairs in the valence shell will repel each other as much as possible. So pairs of electrons in the valence shell repel each other as much as possible, causing the various shapes of molecules. So we're going to use this idea to figure out what shapes different molecules will form. So we'll look at their Lewis structure, and then based on VSEPR theory, we'll determine what the shape will look like. All right, so let's get started. So the first one on your VSEPR theory activity, you should have already completed that, was beryllium fluoride. If some of you have asked me, why are we talking about beryllium fluoride? That's an ionic compound. It is named ionically, however, it behaves covalently. I wouldn't expect you to remember that. If you'd like to understand that more, please come see me and I will discuss it with you. So if you do your NASB, the electrons needed is 20. The electrons available is 16. So shared will be 4, which means we'll form 2 bonds. So you would start with beryllium in the middle, draw fluorine on either side, connect with single bonds, and since we only need 2, we don't need any more. And then we need to make sure everyone's octet is filled. Now remember, beryllium is one of our exceptions. It only needs 4, so it is good, but we need to fill in our fluorine, so we add 3 sets of lone pairs on each fluorine. So this is what you should have had for your Lewis structure. So now I'm going to do a little activity with you with grapes and toothpicks to determine what the shape is going to be.
All right, so let's talk about how beryllium fluoride is going to form a bond. So I am going to use grapes to represent our atoms, and I am going to use toothpicks to represent bonds and lone pairs. So if you look, I have beryllium. Okay, I am going to use a toothpick to represent one of the bonds, and then I will slide fluoride on this end, and then I will use another toothpick to represent another bond, and then I will slide fluoride on like this. Now, as you can see, this is the shape. This one's the first one. It's pretty easy, but this is the shape that we're going to get in order to agree with VSEPR theory. Remember, the VSEPR theory is valence shell electron pair repulsion theory. It says that these bonds, which are made up of electrons, are going to repel each other. Now, the electrons within one bond do spin in opposite directions, so they work together, but we have this bond and this bond want to get as far away from each other as possible. And the way they do that is they form a straight line. This will be 180 degrees. If I rotate it, it's still 180 degrees. There's no orientation that I can produce here where the electrons will be farther away than in another spot. So for beryllium fluoride, our shape is going to look like this. Anyone have any ideas on what we're going to call this shape? What does it look like? It looks like a line, so we are going to call this shape linear. Okay, so this shape, because it looks like a line, we're going to call it linear. The angle on it is going to be 180 degrees. So this is how we're going to draw it.
All right, so hopefully that helped. So let's review. The shape for this molecule will be linear. So we must name it, we must draw it. So the way we draw this is we draw circles to represent the atoms, okay, lines drawing the bonds. We do not have to represent lone pairs when we draw the shape, but we do need to give that angle. So the angle between these sets of, or these bonds, which is with pairs of electrons, is 180 degrees. So make sure this is what your shape looks like when you draw it.
So I also wanted to show you guys some models of shapes as well. So this wouldn't be beryllium fluoride because you can see we actually have two double bonds here. But you can see with two double bonds, there's no lone pairs, and then we have two atoms bonded. So we also get, and you can see this red, blue, red, it's a linear shape. No matter which way I orient it, it's still linear. I like to show these models because you can see the curvature of the bond. The reason this happens is because the electrons are still repelling this way. They still have to stay fairly close because they are bonding the same two atoms, but they repel each other. So here's another example. This would be if you had a central atom with two double bonds on each side. Okay, so this is actually what carbon dioxide would look like. Again, that would also be linear. All right,
Let's look at the next one. Boron trichloride. So the needed would be 30. The available would be 24. Shared would be 6, which means the bonds would be 3. So we'd start with boron in the middle, surround it with chlorine on each side, connect single bonds to each of the atoms. Since we only needed 3 bonds, we don't need to draw any more. Remember, boron is one of our exceptions that only needs 6 electrons, so it is filled. And then we need to fill in our chlorines to make sure they fill their octet. So here's what our Lewis structure looks like. Hopefully you had that for your homework. So let's do the grape activity again and see what the shape for this is going to look like.
now we're going to look at boron trichloride. All right. So we've got one boron, this will be my central atom, and I need to connect the 3 chlorides. So if we go ahead and do it similar to the way we've drawn our Lewis structure, alright, now does this shape agree with VSEPR theory? Do those electrons repel each other as far as possible in all directions? The answer is no. If you look, the angle right here is 90 degrees. The angle right here is 90 degrees between those electrons. However, we have an angle right here of 180 degrees. So these electrons don't repel each other more than these electrons or more than these electrons. So we need to reorient this shape. Even though this is how it looks like in the Lewis structure, this isn't how the molecule actually forms. So we are going to take these and repel a little bit further away from this one and closer to that one, and then do the same thing here. Okay, now you can see that these repel, these repel, these repel, they're all repelling about the same. Even if we look at it three-dimensionally, you can see this angle right here is still the same. Okay, these are as far apart as possible, which agrees with VSEPR theory. Now, if you do your geometry, this would be 360 degrees, and we have 3 equidistant breakups here. So 3 equidistant areas here. So the angle between each of these bonds is going to be 120 degrees, which is 360 divided by 3. All right. Now, the shape, we're going to call this, many of you would probably like to say, oh, that's a peace sign. Let's call this the peace shape, but it is not. If you can see, it kind of looks like a triangle. If you connect the 3 outer atoms, it looks like a triangle, and it is still flat, like the linear shape. So it's in a single plane. So we do call this shape trigonal planar. trigonal representing the triangular shape, planar signifying that the shape does still fall in a flat plane. So this is our boron trichloride. We call this shape trigonal planar, and the angle right here is 120 degrees. So now let's look at how to draw it.
All right, so to review, the shape for this one is trigonal planar. Again, we draw it very similar to the other one. We draw little circles to represent the atoms. We draw lines to represent the bonds. We do not have to represent lone pairs on the outer atoms. And then we must draw that angle, which is 120 degrees. All right, let's look at the next one. Sulfur dioxide. So on this one, the needed was 24. The available was 18. Shared was 6, which means the bonds was 3. We drew our sulfur in the middle, drew each oxygen on either side, connected them with single bonds. However, we were supposed to draw 3 bonds. Now, when we look at our choices of where to put it, you can see that they're identical choices. Bonds are going to choose the choice that requires the least amount of energy, but these are identical choices. So it's not going to be able to choose, and we are going to get a resonance structure. So we must draw the bond in each scenario being with the oxygen on the left or the oxygen on the right, and draw that double-sided arrow between them. All right, now we need to fill our octets. Sulfur does need 8, as does oxygen, so we fill in those octets as necessary. So now let's go look at the grapes and see what this shape is going to look like.
Alright, so now we're going to look at sulfur dioxide. As you saw in your Lewis structure, it has a resonance. When we draw the shape, we only have to represent one of those resonance structures. So let's look at the top one. We have a sulfur in the middle. We connect an oxygen off to one side. Okay, and then on the other side we have a double bond. Now, even though those atoms do repel, they still have to connect to the same atom. So for right now, we're going to look at taking 2 toothpicks to represent the double bond. Okay, and I'll go ahead and do it like this. Okay, to go to the oxygen that's on the left. So we've got our single bond, our double bond. But something we haven't had yet that we have in this example is that lone pair. That lone pair is still a pair of electrons. It's still going to repel. So what I've done is I've broken a toothpick into 2 pieces, and this is going to kind of represent my lone pair. It is a pair, so they do stay together, so I'm going to do it like this. Now, if you can tell, this actually looks similar to what we started with when we did trigonal planar. We have a 90-degree angle here, 90-degree angle here, but we have 180 here. So we're going to approach this one fairly similarly. We've got to move this one down so that these electrons repel a little bit more, and the same with this double bond down here. Alright, so now you can see it does look very similar to trigonal planar, except the top isn't actually an atom bonded up there, it's just a lone pair. Even though it's a lone pair, it does still repel. Now, we don't call this trigonal planar. If we were to look at it and you look at the way the atoms, just the atoms, kind of ignore the fact that we've got that lone pair on top, it looks like a bent line. It looks like we took linear and then we just bent it slightly. Let me turn it this way so you can see it better. So it looks like we took a linear atom and we just bent it. And it was that bending was caused by this lone pair. This would have been linear if we hadn't had this lone pair bending those atoms away. So we actually, ironically, call this shape bent. Okay? The angle is still about 120 degrees. We don't say exactly like we did for trigonal planar because this lone pair actually doesn't repel perfectly as much as these bonds do. They are slightly different, but it's still roughly 120 degrees. So when we signify the angle, we'll use a squiggle sign to represent approximately. So again, this shape is called bent. The angle is about 120 degrees. And now let's talk about how to draw it.
So in review, the shape for this one is bent. It looks like a bent line. So this one's got something different we haven't seen before. We still draw circles and lines to represent the atoms in the bond. Notice we do not need to draw any double bonds. If there's ever a double or a triple bond, you don't need to represent that. You just need to show what atoms are bonded to which. when you're drawing it. This little guy right here, we draw two dots. Okay, this is our lone pair. The two dots represent each of the electrons, and this kind of orb around it, a little circle around the two dots, is supposed to represent the electron cloud, or the orbital actually. The orbital with which those two electrons are going to hang out in. So don't forget to draw the angle. Notice I did the little squiggles. It's about 120 degrees. It's not exactly because of the way the lone pairs repel a little bit differently than the bonded electrons, but this little guy up here represents that lone pair. This leg represents the double bond to the oxygen. This represents the single bond. We do not have to draw two lines. In fact, please don't draw two lines. That's not how you do when you do a shape. You just need to show that there is an atom bonded to two other atoms and there's one lone pair, and then the angle. So this shape is called bent.
Here's another model of this one. I like this one as well. You can see we have our sulfur in the middle, one single bonded oxygen and one double bonded oxygen, and then we have that lone pair. That lone pair is key. It's what causes it to be bent, and you can see this bent shape once I use the model. Again, we have those electrons repelling each other here in the double bond, but again we get that bent shape. Hope that's helpful.
All right, now we have carbon tetrachloride. For this one, needed is 40, available is 32, so shared is 8, and it's going to form 4 bonds. So we draw carbon in the middle, surround it with 4 chlorines, connect everything with single bonds. Carbon's octet is filled with its 4 bonds, so we just need to fill out all the chlorines and make sure they get their 8 electrons. All right, so let's look at the grapes again and see what this shape is going to look like.
All right, next we have carbon tetrachloride. So again, I'm going to take my central atom and we have single bonds connecting each of the chlorides. I'm going to start with it similar to my Lewis structure and kind of see what it ends up looking like. So I'm connecting here. Oh, I need another grape. All right. Okay. Now, pretend this is straight. Okay. Do you think this is right? Let's look. We have like a 90-degree angle here, 90 here, 90 here, 90 here. So we're good, right? Actually, we're not. If we were to look at this three-dimensionally, okay, you might be able to tell that if you look at between this atom and this atom, this is actually 180 degrees. This is 90 degrees, but this is 180. So now we've gotten into shapes that we really have to start thinking about three-dimensionally. We need to get these as far away as possible in equidistant in all directions in 3D. So what we've got to do is we've got to start decreasing this 180 that's right here and increasing these 90s. So the first thing I'm going to do is bring this one down a bit. Okay, bring this one over and bring this one up. Alright, I don't know if you guys can see that. I'll try to hold it out for you, especially since this one's so three-dimensional. But you can kind of see, and I probably haven't made it perfect. I'll show you a model in a minute. But you can see, yeah, this one needs to be a little more angled. I'm pretty close. Okay, so it kind of looks like a tripod with a little stick on the top. Okay, so this way, this is less than 180 degrees, more than 90, and they're all pretty equidistant. So I've kind of created a shape, or no, I have created a shape where all of these atoms, all these bonds, these pairs of electrons are repelling each other equally in all dimensions. So this shape, okay, here, this angle, I know you probably haven't done any three-dimensional geometry before, so I'll just go ahead and tell you this angle is going to be 109.5 degrees. So all of these angles from here to here, here to here, here to here, etc., those are all going to be 109.5 degrees. This shape is based off the idea that there are 4 atoms bonded to a central atom. The prefix for 4 is tetra. So this shape is called a tetrahedral. Alright, tetrahedral. Tetra coming from the 4 atoms bonded to the central atom, tetrahedral. So that's the name of the shape. This is what a model looks like. This angle is 109.5 degrees. So now let's talk about how to draw it.
All right, so in review, this shape is called tetrahedral. This is probably, as we get into these three-dimensional ones, the shapes are a little more complicated to draw. So I want to explain what's going on here. Here's our central atom connected to the chlorine above. So we have that one atom that's stuck up on the top. And the reason we draw the other three this way, these dashed lines represent that it's going into the paper. So these are like going backwards into the paper. And then this triangle that's drawn like this that isn't dashed, so these kind of look like dashed triangles, and this is a filled triangle, that represents that it's coming out of the page. So hopefully you can see a little bit of three dimension here. These two legs are the ones going back into the paper, and this one is coming directly straight out. So this is how we draw tetrahedral. If you have any trouble with this one, just come see me and I can draw it, help you draw it. The angle here is 109.5 degrees. Make sure you include that in your drawing. All right.
So here's a model of the tetrahedral. It's really good to see. You can see it's a lot more stable than my grapes and toothpicks. But I like to show you the models. You can see that 109.5, this middle, the central atom isn't actually touching the plate. I hope you can see that. It is suspended slightly in a tripod sort of manner. But here's the model so you can see it.
All right, let's go to the next one. Phosphorus tribromide. So the needed here is 32, available is 26, shared is 6, so the bonds will be 3. We take our phosphorus, put it in the middle, surround it with the 3 bromines, and connect everything with single bonds. If you notice, we've used all our bonds, so we just need to make sure all the octets get filled. Phosphorus needs 2 more, so it is going to have a lone pair, and then the bromines need to fill out their octets as well. All right, so let's go to the grapes again and see what this shape looks like.
All right, now we're going to look at phosphorus tribromide. All right, we have our phosphorus in the middle, and we have our 3 bromines on the outside. I started with what the Lewis structure looks like, but don't forget we also have this lone pair. So if you can tell, I'm kind of starting with what I started on the last problem. I've got 4 pairs of electrons that are all 90, 90, 90, 90. Looks pretty good, but when we turn it on its side, we can see that we have this 180 degree angle here. So we're actually going to solve this problem exactly like we solved it for the tetrahedral. We're going to take them and kind of orient them at an angle, creating kind of a tripod here, and then we move that lone pair on top, and we get this. So you can see it's very similar to tetrahedral, except the thing on the top is a lone pair, not a bonded atom. All right? So this shape, if you can see, actually looks like a pyramid with something on top. And it's made from 3 atoms bonded to a central atom. So we call this shape trigonal pyramidal, or pyramidal is how some people pronounce it. Trigonal coming from the idea trig, 3, tri, that there are 3 atoms bonded to the central atom, and it's shaped similar to a pyramid, hence the word pyramidal or pyramidal as some people pronounce it. So this angle is still about 109.5. It was exactly 109.5 for the tetrahedral, but like we saw in our other example with the lone pair can't repel exactly as much as a bonded lone pair just because it's a slightly different situation going on. So we say this angle is about 109.5. So the name of the shape, trigonal pyramidal, and the angle between the bonds and the lone pair is about 109.5. All right, let's talk about how to draw it.
All right, so looking to summarize this one was called trigonal pyramidal or trigonal pyramidal. Everyone pronounces it different. In fact, Miss Ward and I both choose different pronunciations, but either one is fine. Here you can see the bottom of this one looks exactly like the tetrahedral. I have the two legs going into the paper with the dashed lines, and then the triangle coming out of the paper. So these are the three bromines here. And then we, just like we did on the bent earlier, we draw that lone pair in its orbital. Okay, and then the angle here is about 109.5 degrees.
Here's a model of trigonal pyramidal. You can see this looks exactly like the tetrahedral, except I replaced that central atom that's on the top with a lone pair. It still repels almost exactly like the tetrahedral. Remember, this lone pair can't repel the exact same way. So the angle is about 109.5.
All right, let's go to the next one. So last one, sulfur dichloride. So needed here is 24, available is 20, shared is 4, which means it's going to form two bonds. So we draw our sulfur in the middle, chlorine on either side, single bonds. So now we've already used up our two bonds, so all we need to do is make sure everyone's octet is filled. So the sulfur has two pairs, which means it has 4, it needs 2 more. So there are going to be 2 lone pairs on sulfur, and then we fill out the chlorines to make sure they have 8 as well. So for the last time, let's go to the grapes one more time and see what this shape looks like.
All right, last one. So sulfur dichloride. As you can see, we've got our sulfur in the middle, bonded, single bonded to our 2 chlorides, and then we have our 2 lone pairs on either side. This is what it looks like in the Lewis structure. Again, very similar to the last 2 we did. We have our 90, 90, 90, 90, but if we turn it three-dimensionally, we can see that we have this 180 degrees here. So that's a problem. Again, we're going to handle it very similar to the way we did with the tetrahedral and orient them kind of in the tripod fashion, except one of our tripod legs is not going to help us out. So we end up with this. Again, if I were to hold it and kind of help that last leg out, this would look like trigonal pyramidal, but it doesn't because this leg can't do anything. So if I turn it, you can actually see, if we kind of bypass looking at the lone pairs for a second, we get a bent line again. So it looks like we took linear and we bent it. As you can see though, this one's significantly more bent than the last one. And that's because our angle is going to be similar to the tetrahedral and the trigonal pyramidal because we have 4 things, okay, repelling each other. Those electron pairs are going to repel, and this angle right here is going to be about 109.5 again. So this shape is actually also called bent, but the way we distinguish it from the other one is this angle and all the other angles, but we're going to diagram this one in the picture, is about 109.5. So it is more bent than the other. All right, let's talk about how to draw it.
So to summarize, this one is also called bent. So the names are the same, but the drawings are a little bit different. Notice we have our central atom bonded to 2 atoms, the chlorine on one side and the chlorine on the other, and then we need to represent our 2 lone pairs on the top. All right? So our 2 atoms bonded to the central atom, and the central atom has 2 lone pairs, so we draw 2 of these little orbitals with their electrons in it. The angle, again, is about 109.5.
And lastly, we have our model of the bent 109.5 version. You can see these lone pairs up here. It is the exact same kind of orientation as the tetrahedral, except we replaced 2 of the legs this time. And I like to bring in the 2 bents for you to see. You can see this one is still significantly more bent than this one. So it's close, but this one is more bent. All right, so this is 120, this is 109.5.
So summarizing all of that up, molecular geometry, the shapes of molecules. We use VSEPR theory to determine those shapes. Remember, VSEPR stands for valence shell electron pair repulsion theory, which means pairs of electrons in the valence shell repel each other as much as possible, causing the various shapes of molecules. So those are the shapes. You are going, for homework, you are going to do part 2 of your Lewis structure worksheet. So you are going to determine what shape they are, draw them, and determine whether they are polar or non-polar. So that's something we haven't looked at yet. So let's look at this chart that's in your notes. This is, we're going to summarize the shapes and talk about how we determine if it's polar or non-polar. So for linear, this is what we draw and it looks like, okay? It's whenever you have 2 atoms bonded to the central atom and you have no lone pairs on the central atom. That means there are 2 electron groups and it is going to be linear. So some examples would be cyanic acid and beryllium difluoride. Oh, I'm sorry. That is beryllium fluoride because it is named ionically. And the generic Lewis structure looks like this. This is like a generic. Linear atoms are always going to be non-polar. However, there's an asterisk. So this is assuming the atoms bonding off the central atom are all the same element. If not, then the molecule is polar regardless of the shape. For the shapes we will look at in this course, that's what's going to be true. All right. Trigonoplanar. This is what this one looked like. It's when you have 3 atoms bonded to the central atom and no lone pairs on the central atom. It will also be nonpolar as long as it is symmetrical, as long as all these atoms bonded to the central atom are the same. Okay? Now, bent is when you have 2 atoms bonded to the central atom and 1 lone pair, and this one is actually always going to be polar. Notice, it says polar, no asterisk. The reason it's always polar is it has this lone pair here. So these atoms that are bent down, they are going to pull the electrons in their direction, or this atom is going to pull it away from these atoms, but this one's least electronegative, so these are going to pull it away, and you've got this lone pair. So this side is always going to be polar, as are these ends, because this lone pair makes it unsymmetrical as far as the way the electrons are being attracted in one direction or the other. All right, tetrahedral. It is when you have 4 atoms bonding and no lone pairs on the central atom. Notice it says nonpolar with that asterisk. So linear, trigonoplanar, and tetrahedral. Those will be nonpolar as long as the atoms bonded to the central atom are symmetrical, are the same. So if this was a carbon in the middle with 4 chlorines, because all those chlorines are the same, it's going to be symmetrical. So that would make it nonpolar. If it was a carbon in the middle and 3 oxygens on one end, a chlorine on the other, that's not symmetrical. So that one would be polar. All right. Next, trigonal pyramidal. This one will be polar because we have that lone pair on top. So similar to the bent up here, these atoms will pull the electrons more in their direction, and we have this lone pair up here, which isn't going to move, so we will have a polar atom. We get trigonal pyramidal when we have 3 atoms bonded to the central atom and 1 lone pair on top. Lastly, we had bent, and this is the second bent. This is the bent that has an angle of 109.5. It is when you have 2 atoms bonded and 2 lone pairs on the central atom. It too will also always be polar because it has that lone pair, those 2 lone pairs on top, so the electrons will always be pulled slightly more in this direction. So let's go look back at the examples we did earlier in our VSEPR theory activity and determine if those are going to be polar or nonpolar. So beryllium fluoride, notice we have a linear, which we have to determine whether it's polar or not. But since it is symmetrical, you can see the fluorines are on both sides. They look identical. It is going to be nonpolar. Let's look at the next one. So for boron trichloride, it is trigonoplanar. We have to determine whether or not it is polar or nonpolar. However, all 3 atoms that are bonded to the central atom are all chlorine, so it is going to be symmetrical, so it is also nonpolar. Sulfur dioxide, it has a lone pair on the central atom. Anytime there is a lone pair on the central atom, that automatically makes it polar. So sulfur dioxide is going to be polar. Carbon tetrachloride, it's a tetrahedral. This one has no lone pair, so we do have to determine whether or not it's polar or nonpolar. So if you can tell, all the chlorines on all the sides are the same. So this one is symmetrical, so it is going to be nonpolar. Phosphorus tribromide, it has a lone pair on the central atom, which automatically makes it polar. And last we have sulfur dichloride. It has 2 lone pairs on the central atom, so that one is also going to be polar. Again, anytime you have any lone pairs on the central atom, that molecule will be polar. So this one is polar. So summing it up, if you want to understand this table, this column is when you have 2 lone pairs. This column is when you have 1 lone pair. And this is when you have 0 lone pairs. This is all talking about how many lone pairs are on the central atom. This, if you can see, is written at an angle. So this diagonal right here is when there are 2 atoms bonded to the central atom. This diagonal right here is when there are 3 atoms bonded to the central atom. And this is when there are 4 atoms bonded to the central atom. So using it, you can see bent right here is when you have 2 atoms bonding and 2 lone pairs. So you're going to get a bent shape, which is going to be 109.5 degrees. So hopefully this table is helpful. You can see that the little shapes are drawn here. These are models similar to the ones I showed you along with the grape demonstration. But hopefully this will help summarize the shapes that we learned today.